In this video, we're going to be doing some spherical and cylindrical coordinate examples for multivariable calculus. So the first set of problems is like find the limits of integration for the triple integral of f of r and theta and z times r dr d theta dz, which means that we're doing cylindrical over the region that's described. So we are interested in getting the limits of integration for the triple integral of f of this times all of that. Okay, which means that we're working in spherical coordinates. So x squared plus y squared is less than or equal to 4. I'll just kind of copy down that information we're given. And z is between -1 and 2. Whoops, pardon me. -1 and 2. Okay. So I'm going to say, all right, this is x squared plus y squared, that's r squared. R squared is less than 4, means that r is between -2 and 2. But really, if we're talking about the inside of a disk, we're just going to say r is between 0 and 2. And theta is going to run from 0 to 2 pi. Because we're talking about the full disk here. And then z is going to be running from -1 to 2. So that's the same, right? We know that cylindrical is just polar with z attached. So I'm just going to be triple integrating. We can just start with r, because all three of these are numbers, so best case scenario. So from z, we're running from -1 to 2. And theta, we're going 0 to 2 pi. And in r, we're going from 0 to 2. And we're integrating f of r and theta and z times r d theta dz. Okay. That was the setup. Is that going to be not covering the whole thing? That's just the thing for us. For number 2, it says lower hemispheres of a sphere with radius 2 centered at the origin. Why would you integrate over a sphere with cylindrical coordinates? I'm realizing that's okay. Okay, so I don't even know how to draw this. The lower hemisphere of a sphere with radius 2 centered at the origin. All right. So what we really need is, I guess it's going to look like that. This is going to be the kind of the XY plane that I drew in on top of it. And, it's probably going like that. It's pretty nice. Okay, so, that's, well, it's all right. That's the sphere. So it looks like, okay, the radius is 2, so r is going to be running from 0 out to 2. Theta going from 0 to 2 pi, right? The image in the xy plane is still a circle with radius 2. Its z is running from the bottom of this sphere up to z equals 0. So I need to just write an equation for this sphere and, get z equals some. Let's say, all right, this sphere with radius 2 is the set of all points where x squared plus y squared plus z squared equals 2 squared. If I go to solve for z to get the lower half, I'm going to have z equals the square root of 4 minus x squared minus y squared. Okay, but this is a positive number, and I'm interested in where z is negative, so I take the negative square root. Okay. And so I guess this is going to be my lower bound for z. My upper bound will be up here on the xy plane, where z is equal to 0. I should have given it some labels. And yeah, so I think what's going to happen here is I'm going to have r running from 0 to 2. I'm going to have theta running from 0 to 2 pi, because it's the whole circle up here with radius 2. And z is running from the negative square root of 4 minus x squared minus y squared all the way up to z equals 0. Okay. This is one that would be much better off integrated using spherical, but it's okay. So we're going to triple integrate z. Okay, we're going to have to reverse the order, right? Because z depends on both x and y here, so that has to be the innermost integral. So I'll just, kind of switch the order around a little bit and say, all right, let's do r on the outside. Then theta. And then z. So from the negative square root of 4 minus x squared minus y squared all the way up to 0, I'm going to be integrating f of r theta z times r. This is dz, d theta, dr. The next couple questions is the same idea, but now we're going to switch to spherical coordinates, and we know that because we're seeing rho and phi, and that only comes up in spherical coordinates. So, and we're going to be integrating over the following regions centered at the origin. Number 3, sphere with radius 4. Okay. Well, if it's the whole sphere, we know that the sphere is, okay, rho is going to go from 0, that's the origin, out to rho equals 4. That's set of all points 4 units away, that is the sphere. We let theta go from 0 to 2 pi, and we let phi go from 0 to pi. So I'm going to say, switch up the code. I'll say I'm going to triple integrate, but because all of these are going, from one number to another number, I don't have to really concern myself with the order of integration. I'll just start with theta on the outside, so it's 0 to 2 pi. After that, we've got phi, and that only goes 0 to pi, because that traces out the full circle. Okay. And also, rho going from 0 to 4, because the radius is 4. F of rho and theta and phi, rho squared, sine of phi, d rho, d phi, d theta. Number 4 is the region between the spheres of radii 4 and 5. Okay. Well, I think that all that's going to change is that, we're going to be taking the full shell, but we're just not going all the way back to the origin. So instead of going from 0 to 4, I'm going to go from 4 to 5. Okay, I just didn't really stop to think about how these problems were going to play out when I assigned them. This is a little too similar. Yeah, that's good. I was not sure what I was looking at or thinking about. Lower hemisphere of the sphere with radius 2. This is going to actually involve some thought. So, with rho equals 2. Okay, well, I actually already drew that once. So I don't know, I think I threw it away. But if I'm looking at the lower hemisphere, okay, just on the z-axis, right? Okay, and we're starting with that's not the best, but it'll be all right. Okay, up here, this is where phi equals 0. All the way down here is where phi equals pi. So over here, the xy plane, which is this circle that I drew, and I need to make it way wider, more of an ellipse to get the perspective right. That's the xy plane. That's z equals 0. That's also where like phi is the angle between, I guess, my pen and the z-axis. And so when I go all the way down to the xy plane, that's where phi is pi over 2. So it starts at pi over 2. I'll even try to draw something. There, all the way until there, which is phi equals pi. We don't let it go beyond pi because really, okay, you know, if this is where x is positive, you know, something back over here is where theta is, I don't know, maybe near 2 pi or near 0, but phi is near pi, right? And so we can take care of the difference between that point and that point, which would have the same phi value by the difference in their theta values. All this to say, all right, phi is running from pi over 2 up to pi. Rho is going from 0 to 2. And theta is looking like it's going to go from 0 to 2 pi because, like that, because it's the full lower hemisphere, right? We didn't like cut it off there and, you know, cut it out and have 3/4 of it or anything. It's the makes its image in the xy plane is a full circle also, is how you know. So now I'm ready. I'm just gonna fill this in. Okay, these are all just numbers, so the lower hemisphere would be, okay, theta 0 to 2 pi. Phi over 2 to pi. Rho 0 to 2. F of rho theta phi, rho squared sine of phi, d rho d phi d theta. And yeah, that was all of those. Right, number 6. A sphere with radius 3 has volume 36 pi. Okay, that's true. So find the value of the integrals. Okay, so theta going from 0 to pi, phi going from 0 to pi also, and rho going from 0 to 3. So rho phi theta. All of these are rho phi theta. Okay. So with this one, what we're saying, like to kind of translate this into English, is that rho is running from 0 to 3. Phi is running from 0 to pi. And theta is running from also 0 to pi. Okay. So I know it's kind of like it's a part of a sphere, right? Because we're running rho from 0 to 3. And that's what we're doing, is figuring out how much of a sphere is this, and then, you know, dividing 36 pi by the appropriate amount. So if phi runs from 0 to pi, that means that we are getting the full up and down of our circle. Of our sphere, pardon me. Okay. And if theta is running from 0 to pi, that means we've only got half of it, I think. Right, and imagine this being the origin, and okay, I probably should have, this would also be the x-axis, so I'm, you know, we're looking at this probably the wrong way. Let me see if I can draw that again. If I give it a little bit of slant, is that what I'm looking for? I do not think so. That's even worse. Either way, it's half a sphere. Okay, pardon me. Wish I could, like, that's the x-axis. It's getting worse and worse and worse. I'm just going to stop on behind and say this is half of a sphere. As a result, the volume, which is this is a triple integral of dv, that was the other thing I was going to point out, rho squared sine of phi d rho d phi d theta, that's just a big expression for dv, and if you triple integrate dv, you get the volume. So it's going to be the volume of this half sphere, which is going to be 36 pi divided by 2 is 18 pi. Okay, let's get those drawings off screen. That's really bad. All right, 0 to 2 pi on theta, 0 to pi over 2 on rho, on phi, and then rho going from 0 to 3. All look the same. Okay, so if theta is running from 0 to 2 pi, we're going to have the full, full way around. In x and y, we're getting the full circle. It looks like maybe in z, we're not. 0 to pi over 2 on phi, that's the upper half of a sphere. That's the set of all points where, the angle from the z-axis to the point on the sphere is, well, less than pi over 2. So it's going to be over there and this as well. So I think I'm going to be able to draw this one. It's going to be this one. Okay, might have been worse. Hey, what's up? And I'm feeling like since this is another half of a sphere, it's going to also be half of 36 pi, which is going to be 18 pi. What time does this class start?
37.
Okay, I still got some time. All right. But I've lost my problem set. That's not it. Right. And then this one, number 8, what's going on here? So theta's only going 0 to pi over 4. Let's see. Sure. Hold on just a second. All right, not sure where I left off there, but let's see, I've got this. I'm working this problem. It's much later in the day. I've got, okay, rho going from 0 to 3. Okay, this is dv. Okay. Phi going from 0 to pi over 2, which means I'm only dealing with the top half of a sphere. And then theta going from 0 to pi over 4. Oh, I know what this is going to look like. It's like part of a bundt cake. I don't know how else to describe it, but like I can just see it in my head. So I'm going to draw 0 to pi over 4, but we're going to assume that pi over 4 is going to be about like that because, my y-axis is going to need to come in about there. And so this is x, this is y, this is the line y equals x. Maybe it's supposed to be a little more like that, but whatever. Okay. We're looking for the part of the sphere that sits up above here. So it would look like, if z was over here, and say it was about like that. That was lined up a little too nicely, but it's that part of the sphere. So it's going to be half. So if it was twice as much, it would be an 1/8 of a sphere. Let me think about it. Yeah, because if I went, instead of from 0 to pi over 4, I went from 0 to 2 pi on theta, that would be 8 times as many pi's, right? I would have the entire top half of the sphere. So I'm looking at 1/16 of a sphere, so this is equal to 36 pi divided by 16. That was a little tricky, but that was a good one. I liked it. Okay, lost my black pen. Okay, number 9. Oh, another one of these. Stuff out of the way. This is plugged in. This must be. All right, number 9. Negative pi over 4 to pi over 4. On theta. Phi going from 0 to pi. Okay, so that's the full circle. And where is it? Rho going from 0 to 3. Oh yeah, I knew that already. So rho squared sine of phi d rho d phi d theta. Okay, so we're integrating dv over this region. We just kind of got to interpret how much of a sphere it is. Okay, rho running from 0 to 3, that's not telling us anything new. Phi going from 0 to pi, so that's the full, vertically it's the full sphere. It's just along in the xy plane, we're only going from negative pi over 4 to pi over 4. This kind of draw maybe the top, very top view. So that's pi over 4. There's negative pi over 4. Okay, we go out to rho equals 3. Well, that's just going to be like that, where that intercept right there is 3. And we're really looking at it from the top. Okay, so in some sense, it's going to be a quarter of a sphere. Okay, this is the top view. I might take a risk and try to draw this for you. Trying to think of what perspective I want to draw it from. That's just as bad. I'm really having a tough time drawing. I can see it in my mind, but I cannot draw it. So I'm just going to have you believe me on the fact that I think this is the best evidence that it's the quarter of a sphere. It's going from 0 to pi. It's the full range of phi. And theta going from negative pi over 4 to pi over 4 is just a quarter of what it could do in total. So yeah, I'm going to say that this is 36 pi divided by 4 is going to equal 9 pi. That was a good set of problems. Number 10 says describe the set of points. Right? Oh yes, I remember this is related to a question I took in class, and I realized I could make some problems out of this. So 10, if theta equals 0 and phi equals pi over 2 and rho is positive, okay, then we've got, the question is, what are we looking at, right? So theta equals 0, that's the x-axis, right? It's when rho is positive, it's the positive x-axis, and when rho is negative, it's the negative axis, the x-axis. But, like, how high up are we talking? Well, when phi equals pi over 2, that gives me the knowledge that I'm in the xy plane, right? Because if it goes, okay, positive z-axis is phi equals 0. If it were to tilt down to pi over 2, that would be horizontal. That's basically where z equals 0. And then beyond pi over 2 and going all the way to pi, that's where you're in the negative z territory. Okay, so 0 pi over 2. Okay, so theta equals 0 is x-axis. This is in the xy plane. And rho greater than 0 is telling me that I'm on the positive x-axis. So all in all, this is this set of points. The positive x-axis, and I might even just indicate that it is not including the origin, but it is the set of all of those points to that side. Okay, so x, y, z. Okay. 11. Theta equals pi. Okay, so that's also on the x-axis. phi equals pi over 2, rho is greater than or equal to 0. This is not very different, but that's okay. Okay, theta equals pi, that means we are on the x-axis. Or, let's see, or above the x-axis, depending on this, right? So phi is equal to pi over 2. That means I'm in the xy plane. And rho greater than or equal to 0 means, okay, I'm going in the direction I expect. So theta equals pi. That is generally where we've got x being negative to the left of the origin in the two-dimensional case. So I'm going to call that the negative x-axis. So if I was going to draw this, I'd draw most of my x-axis, all of my y-axis, and then my z-axis there. And the one that I'm talking about, it includes the origin, but also where x is negative. Okay, so it's that set of points. And number 12, which I think is, yeah, it's our last problem. That's phi equals 0. And rho greater than or equal to 0. Oh, I see what that is. Okay. Well, where phi equals 0, that's probably along the z-axis, right? But if phi was equal to 0, well, it's definitely along the z-axis. I was thinking of the positive z-axis. If phi was 0 and rho was negative, we'd be down on the negative z-axis. But knowing that, I know that it is not the x-axis, not the y-axis, but it is the z-axis. So that's the set of points that, fits that description. And for, well, I think any value of theta, that's going to be true. Okay. Yeah, that's all the problems for this problem set. Let me make sure. Let me scroll down. Yeah, that's all. Okay. In the next problem set, that's when we're going to actually run some integrals where we have to convert to cylindrical or convert to spherical coordinates in order to evaluate the integral. But for now, we're just kind of getting used to the coordinate system. So thanks for watching.